So your next presentation, of course, I'm not going to waste time. So please go ahead to complete it within the time frame. Thank you.
Okay. So hopefully, like everyone is pleased with the progress we did in the maturity project, because we don't have as much of progress in this one. So this one, it's a little bit different project. It's a complicated one, and it's a very visionary project that we are looking, into an autonomous drone-based system for seismic response monitoring of bridges. So I have actually 3 people working on this project. So 2 of my previous postdocs, like Luna, she worked on vision-based monitoring, and she is the post-processing, expert when it comes to using videos for informing infrastructure, structural health and response. Ejam, she is expert in technologies, and she was actually our drone pilot, and she's the one that flew the drone in our labs. And then I have a new graduate student, Muni, a master student, who will be looking into the synthesis of the existing technologies and see if she can also, continue what Ejam and Luna did. So the introduction, is that drones, and the first 5 slides almost are the same as the previous presentation, but I promise I will show you some interesting videos and new stuff towards the end. But to set the stage for this, the introductions that drones, many of the hot technologies, if you will, are on the rise, and in the bridge community people are using it. I know some DOTs now, I think Utah, for example, they have almost a department, for UAV inspection, and they have so many trained pilots now that they can function a fleet of drones, not only 1 or 2, maybe more than this. So UAVs or drones in short are are getting more popular within the bridge community. So if we were to leverage this further, that's the vision that I'm hoping, to accomplish through my career, if I can, to tie to the hazards, and specifically the seismic hazards, if we can have an autonomous or semi-autonomous real-time or near real-time, it depends on the limitations that we have, decision-making, framework. So when you have an earthquake in California, they do have now these early warning systems that you can, if an earthquake, is sensed in the 30, 40 kilometers below the surface of the earth, once the waves are generated, you can actually trigger some early warnings that can reach the surface and reach even the critical infrastructure maybe 20 to 30 seconds before the earthquake hits, which is not a lot of time, but can be enough time to, let's say, launch a drone. If you have a drone or more than one parked on important structures, the Bay Bridge, for example, or the Golden Gate Bridge in the Bay Area. If you have some of these drones parked there, and they would receive, their control stations would receive these signals, maybe the drone will launch to a predefined place, and by the time the drone is ready to shoot the video, the earthquake starts and the structure start vibrating. You can collect the video of the vibrating bridge or structure, feed it to the cloud, and use a digital twin or any type of these technologies to see these displacements that the drone captured. The drone will capture a video, the video will be processed to understand how much displacements the bridge saw during the earthquake, and using a digital twin you can interpret this displacement. Is it a red flag or not? Then you can make a decision on this bridge. And if you do the same thing for several structures or several important bridges on a network, you can have a good idea of how the system, and plan your emergency response accordingly. Maybe go to this route, don't go to this route, this bridge needs immediate attention, this one doesn't need as an immediate attention, and so on. So as I said, it's a very long-term vision, and it involves a lot of components. So this project will just provide some preliminary or foundational work for realizing this vision. So how is this related to ABC? I answered this question before. It's not necessarily ABC in terms of the technology itself, but it's it has to do with the fast response and the immediate decision making, and immediate traffic flow decisions associated with bridges in case of extreme events like seismic. So this is what we have in terms of the relevance to the ABC. We built this project based on our work on conventional vision-based monitoring. So we have done a lot of work for dynamic and seismic response monitoring using conventional, not conventional, stationary cameras. And, this is some of the bridges we tested. We tested 2 or 3 bridges. I think when I started at UNR, there were several tests here that we monitored. We even, developed some repetition in this area, and we were invited to Japan, and we were able to monitor a full-scale, test in Japan. So we have developed our own in-house tools for post-processing videos using stationary cameras to inform structural and seismic response. But like we always use, like as we do our work, we always face some challenges, and that's why we need to do research along the way. So in this specific project, for example, like you see a nice like illuminated picture here, but the camera, when you adjust the camera setting for the right like digital image correlation and video monitoring settings, this is what the camera saw. So it's dark image, like, and all the registration of the targets that we are trying to track here failed. So we needed to do some side research to develop, to provide image enhancement like frameworks, and we were successful in doing this. And eventually we were able to get the result that we were hoping from this building. So this is to give you an idea how, like challenges arise during research and what we do to, overcome these challenges. And that's exactly what we are going to do for the drones. So the objective, of this project is to do some VNV, validation and verification tests for using the drone videos. We are not into the drone technology yet. We just want to shoot a video with the drone and see what we can get from this video. It's this as simple as this. So, the tasks that goes this in general, what are the existing methods and technologies towards the autonomous, drone-based dynamic response monitoring. So the drone launch, these type of things, we are not going to do research in this area, but at least we wanted to collect the data, or collect not the data, the state of the art in this area, and then do some small scale tests that we can use for some verification, and large scale tests which I will show you now what type of tests we did, and eventually try to come up with some guidance on are drones, simply easy to implement for dynamic response monitoring or not. We use drones already for visual inspection. Drones fly around bridges. They can zoom in and out from connections and see loose bolts and all the cracks and all these type of things. But what we are looking at here is a larger, response, which is dynamic response of a full vibrating structure. So that's what we wanted to assess in this project. So the first test, these are the different components similar to what I presented in the resilience project. And we always identify all the different categories of science, if you will, that are associated with a specific research problem, and see what we can learn from this. Obviously, there is no single student that can cover all these and absorb all this knowledge just as part of their thesis or so, but we try at least to start from a 37-foot view, see all these different components that we need to have this framework, and then at the end of the day, we are realistic and we just pick a couple of these important areas and do a good synthesis to benefit the bridge engineering community. The second task is to do small scale tests. So these are some of the toys, if you will, that we have in our lab. That's a small lab, not our big lab. And we wanted to to fly a drone and vibrate this small structure that you see here, for example, and see if we apply a sine wave with a known displacement and a known frequency, can we reproduce this results if we shoot a video using a drone. So that's an example of one of the tests that we did here. So that's the drone flying. And as you can see here, the drone starts drifting, and this is exactly the type of challenges that we will be trying to resolve when we do the post-processing. So that's one example. We are still, we collected the videos, we conducted the test, but the post-processing will be ongoing for the next few months. Again, this is not simple, just a small short video like this might need, a few weeks or several months just to get something meaningful out of it. The good news is that, we had a very large scale test, a very actually interesting and unique test that happened in our lab a couple months ago, and I was able to get the permission, to monitor this with a drone. So I'm sharing with you a short video again here, just a few seconds from the test, and just take a look at the drone. See the drone here, how it shifts. Unfortunately, I was just shooting this video from my phone, so it's not the video itself is not stable or stationary. You can see even my reflection here, but you will be able to tell that the drone is drifting, and I will show you in the next slide what this drifting look like. So you see here, that's the shake table test. It's a bi-directional text, and it's two tables actually. Let me play it again, and that's the drone, shooting a video in the plan view for the test. So that's the video again, and you can see here the drone is swaying, and sometimes actually you see plus or minus 6 inches jumps. So what did the drone see for this test? That's what I have in the next slide. This is what the drone, you know, like saw in a test like this, and that's what we recorded from the drone. And so again, when I play the video, I have this mark, this, you know, like yellow target for you. That's a stationary point. So this black box is a stationary, you know, like box sitting on the lab floor. So just keep your eyes, you know, like, and I will play the video a couple times if you want also, you know, like just keep your eyes on this yellow circle. That's a stationary point. If it's not stationary, this means that the drone is swaying, and you will see what type of swaying the drone is doing here. And when I play the video. So you can see the table is moving like bidirectionally. That's an El Centro earthquake, you know, like in two directions. And you can see here that, you know, like the drone is shifting, and you will see even a big twist now. You see, that's the twist that I was talking about. Again, this is all, you know, like something that we cannot control. You launch the drone and you start shooting the video, and it's the aerodynamics around the drone, like, you know, that and the drone stability itself that will do this. So speaking of challenges, similar to what I showed you for the Japanese test, when we ended up with, you know, like a side research to enhance these pictures, that's what we are working on now. You know, like we know that drones drift, and because of the wind and because of this, at the end of the test, that's the end of the video. You see, at the end of the test, we even, like, you know, completely even missed this target. So we have plus or minus, you know, like 5 to 10 inches in the plan view, maybe not 10 inches, maybe plus or minus 5 inches. So can we use stationary points to correct for the drone, you know, like shift and correct the response itself, you know, like using this data or not? So that's what we are going to learn in the next, you know, like 6 months, I would say. So I'm hoping that there might not be a chance, you know, like to do like another research day from this project, but I'm hoping that if we can complete and get again some promising results from this test, you know, like within the next 6 months, maybe this would be an interesting topic for like a research webinar. Then we can do a full 45-minute presentation like from this project. Again, it's research, so we cannot know yet if we will be successful or not, but I'm sure that this is a very interesting and promising, at least, you know, area, and we would like to pursue as much as we can research in this area. So, you know, like the timeline for the remaining work, you know, like the synthesis of the drone technologies, that's the master since she's working on now, Muni, and hopefully she'll wrap up like a nice draft by the end of the spring. The post-processing is ongoing, but again, I don't want to overpromise. I think we'll need like few months to get something meaningful from the small-scale test that we did, similar to the one that I showed you, and even more time, you know, like for the large-scale ones. So we are hoping that, you know, like by the end of the summer, we will wrap up this project. So I think this time I did well in time, so we can take few questions, I guess.
Thank you very much, Dr. Mustafa. Yeah, that's interesting topic, use of aerial vehicles, and as you showed, there is always movement. And we have a question asking what would be the impact of the wind, because you were in the lab and there was so much of
yes
movement, but if you are out, I've tried myself with the toy drone, the wind is terrible. So what would be the impact of the wind?
Oh yeah, this is a very legitimate question, and that's the most, you know, like the biggest concern, of course, you know, like for like drone use. So there are two, you know, like things that I know to the best of my knowledge that might help, you know, like answering this. You know, like thanks to nature, you know, like when you have a big earthquake, like we are thinking about events of earthquake, you will not have at the same moment of earthquake, you know, like large wind speeds. And I think this is, I think, nature. Like maybe you guys can double check on this, but that's what I personally know since I was a little kid. When at the instant of an earthquake, you will never have like this 160 mile per hour type of winds, for example. You will still have minor winds. So the minor winds, that's the second part. There are already most of these drones. What you see here is, you know, like the drone trying to stabilize itself. So although that's when the drone tries to stabilize itself, it shifts, you know, like back and forth or jump up and down. So that's what the drone would do in a real like life scenario as well. So what you see in the lab will be exactly similar to what you'll see in a medium or a small, you know, like wind speeds. So the drone is just, they have all these built in, and of course there will be more and more, you know, like enhancement and control like algorithms as we the computer scientists are working on this, I think, tirelessly. But like what the drone did in the lab is trying to correct for itself position. It will do it in I would say up to speeds, like some of these drones, they are rated for maybe up to 40 maybe mile per hour winds. So what you see in the lab will be exactly what you will see in the wind. Again, this is a hypothesis. I'm not sure. We didn't go and try this in the lab yet. in a field yet, but that's from what we read in the literature. That's what we expect. And again, these are the wind speeds that you would expect in an application like this when you monitor a bridge during a vibrating structure and in case of an earthquake. But if it's a hurricane and a wind, like extreme wind event, then I don't think drones can be used in this case.
No, I think you're right, Dr. Mustafa. Again, I'm not any expert in this, but I have seen some reports. As you go for more expensive drones and more equipped drones, you will have, I've heard that that gyros that they use, they are so sensitive and so good that you may get even better stability than what you showed with maybe doubling the price of what you paid for that drone.
No, I agree. Yeah, that's true.
Yes. So, let me see if I understood. So, your challenge will be what? To make sense of that video that you took. No, how would that be done? I'm guessing,
we have, I'm sorry, did you finish your question?
Yes, no, I'm guessing image processing or things like that, but can you elaborate?
Sure. So, there are, different things we do. Whenever we do like an experimental test like this, we always look for a ground truth. So we have always data from mechanical sensors. In case of the small, tests, we know the input of the small shake table or the sine wave frequency. So when we process the video and get the sinusoidal response of the structure, we can compare this against the input that we give to the table to know if we capture the right frequencies or not. In case of the large scale test or the full scale test of the pipelines that you have seen, we have, I don't know, they used probably like 30 wire potentiometer. So we know the exact displacements at most of the locations where we have our targets. So at least we know what is the right answer using mechanical sensors. And we will, strive to reproduce this answer from the drone's video, either, by correcting for the drone motion itself using stationary points. So there are several objectives that we wanted to do here from this video. First of all, how to stabilize the video. Are there, post-processing tools to stabilize the video beyond the mechanical tools that are built in the drone already? Because what was built into the drone, it did a job already. By the time we get the video, that's all what the drone can do. So the next step is to do this in the post-processing. So I think even MATLAB now, we have some black box type of tools for drone video stabilization. So we will try to do these stabilization videos and see if they make any difference. The second thing is that the image processing itself, the targets also, when you have the targets not in its place, if the drone shifts and you do a digital image correlation post-processing, algorithm, the digital image correlation, you look for targets in the vicinity of several pixels, because of the drone shift, the target is not in this vicinity anymore. So we really need to see if the DIC post-processing algorithm would even work for these big, changes in the target locations or not. So I would say these are the two main challenges that we will try to overcome when we do the post-processing and provide at the end of the day some recommendations on how to post-process drone videos and how to which mathematical methods is the best to get accurate results.
Thank you very much, Dr. Mustafa.